All right, recording is rolling. It's Wednesday, March 29. So we're going to take today to work more on this page from yesterday. We'll do some more circuits and some more of these Kirchhoff tables and waterfall models on the back of this page. And then tomorrow, I'll get you guys set up with the lab. It's going to look a lot like these Kirchhoff tables. Yesterday, I showed you guys how to use the multimeter. I'm going to break that out again today and remind you guys how to use that. And then tomorrow, you guys will get you that. Okay. So before I get going too far, we do have a video demo lined up. So let me switch my screen over, show you guys this. Okay. So this breadboard here. So a breadboard you can plug electrical components into. Now you have to know how it's wired on the backside, and I'll show you guys that too. So that you know how to plug stuff in. But real quick thing you can make a robot with, if you plug in the right components, right? Got the resistors in the right place, the capacitors, inductors, and the voltage source, and the little wheels and components, right? Create something like that. Okay, so yeah, let's look at that real fast. Now I've got a poster for that. Here we go, breadboard. Right, so got all these places to plug components in, and if you flip it over, which mine has a sticker on the back, but this is what it would look like. Right? We've got these metal wires. Now, it's good to know that these five are connected, these five, and so on all the way down. Right? But there's a gap in between, so you can like bridge the gap with components. This is a common thing to do. Right? And then there are these couple of metal strips here and a couple of metal strips here that run along the entire bit, and that's called along the entire breadboard, and those are called buses, right? So, term for those. Okay. So like you would here, let me give you guys a counter example. Like if I have this LED, I would not want to attach this LED like here and here. That would be completely pointless because there's a wire running underneath those two leads. So it would always short it out. Like there's no way this LED could ever turn on. It would always be shorted out. You guys remember that short from yesterday? That wire that path of least resistance has zero resistance, right? But if I bridge this gap, now you guys know there's a wire running under here, and then there's a gap, and then there's a wire here. So I can connect these leads. Okay. So I had yesterday the cell phone charger. I got 5 volts right here, 5 volts. So let's see what happens if I connect these leads right here. Right. Oh, it'll turn on, right, this LED. Okay. I should tell you guys too, LEDs are polarized, so they only work one direction. So if I switch these leads, if I switch the red and the black, it actually will not turn on. Oh, right. But if I switch it back to how they originally were, yay, got an LED. Right. That's a very simple setup there. Okay. Let's look at some review stuff. Right, flash some of these up here. So we were starting looking at these Kirchhoff rules. Now, Kirchhoff only had 2 rules, really. He had what's called the loop rule and the junction rule, right? But all these other rules kind of fall out of those, so I just throw them all up on here, right? So loop rule says if you find any loop, this loop, this loop, this loop, this loop, the voltage just have to sum to 0. And the junction rule says if the current ever splits, which would happen like this type setup, right, then the current has to sum up, right? And then, all these other rules fall out. We're going to use those today. I'll also remind you guys how to use this multimeter. Okay, so I got a multimeter right here. Right, you can use this to measure the potential difference in volts, but you have to connect that in parallel. You can use this to measure the current through any point in the circuit, but you have to break open your circuit and force the current to flow through it. So that's connecting it in series. Okay, I did that yesterday. I'll do that again today. So you guys know how to do that. Right. So there's a few posters anyway. Okay. It's warmed up there. All right, put this aside. All right, let's do this. Let's hit a few of these, and then this one, and then we'll flip over to the backside and do a couple of those on the backside. Okay. So number 5, you guys see number 5? Ooh, I got 3 resistors lined up. Now, those 3 resistors, are those in series or parallel with each other? They're all in parallel, right? The current has to split 3 different ways. Okay. Let me show you guys what that looks like. That one. Okay, here we go. Okay. Here's 3 resistors that have all their leads tied together, okay? Which is exactly what it looks like on number 4. Okay? And then if I connect the leads of the voltage source, What happens? Right. And they're all really bright, right? Same thing as Paul Hewitt did that. They were all really bright. Right? But the question here for now is, what is, and I'll save the multimeter for later, just got so much class time, right? Is what is the equivalent resistance? Right? So I'll walk you guys through two different ways to do this. You guys might remember one way is fraction method. And that might actually be the fastest way for this one, just use the fraction method. 1 over the total resistance. Now, my numbers are different than your numbers, but all our circuits look the same, have the same geometry. So you can use the same procedure that I'm using. Okay? And my resistors are 8, 10, and 12 ohms. So I'll go 1 over 8 plus 1 over 10 plus 1 over 12, right? You guys do the same thing with your resistors? Okay? So everybody good so far? And I'll eventually pick this paper up from you guys and grade it. So as long as you're following along and you're getting the correct answers, should be all right. You could get common denominator that you get kind of messy. I'm just going to break out a calculator. You guys have calculators. So that plus that plus that. Okay, I'm going to get a wacky decimal. Just go ahead and jot that down. So some crazy decimal for a unit. Okay. Now that's not the answer yet. That's 1 over the answer. Remember, because the reciprocal, right? Okay. So there's still one more step you have to do, which is you have to take the reciprocal of that. Right? If you like, there's a key on your calculator right above the 7 says x minus 1. Right? And that will take the reciprocal for you, right? Or you can just type that. Okay. I'm getting this many ohms. That many ohms. Okay. So that's an answer choice. Bam, right there. It's an answer choice. Okay. Okay. So it's as if there's a single resistor that has that much resistance, like that many ohms, that the battery is pushing against. Okay. Do you guys good so far? Okay. So I'm going to do too. I'm going to solve this the other way you could solve resistors in parallel, which is the product over sum method. But remember, product over sum, you can only use that for 2 resistors at a time. Okay? Also, since there's more than 2 resistors, you have to use this procedure where you start on the opposite side from the voltage source, work way back towards the voltage source. Right? This one technically doesn't make a difference, but it will on other circuits. So I'm going to stick to that practice. So here's the 2 resistors furthest away from the voltage source. I'll start with those. That's R2 and R3. So I'm going to say the resistance equivalent is the product over sum of those 2, which in my case, 10 and 12 ohms. So I'll do product over sum of 10 and 12. That's like 120 over 22, which is 5.45 ohms. Right now, that's just the middle step. Now I'm going to redraw the circuit. We did one of these yesterday where it was a multi-step process. I had to keep redrawing the circuit. Okay. So voltage source here. R1 I haven't touched yet. So for my paper, it says 8 ohms. Go ahead and write that in. Okay. But R2 and R3 are collectively 5.45 ohms or whatever you got on your paper. Right there. Okay. Working my way back towards the voltage source. Now these 2 guys, series or parallel, have to be parallel. I mean, we kind of said that already, but if you weren't sure, anytime you see a junction and the current has to split, that's a sign it's going to be parallel. Right? It's pushed both simultaneously. Right? If you're driving around town, right, you pick a road, say, do I want to go through that stoplight or that stoplight? Right? It's not both sequential; it's either or. Right? So I can do product over sum of these 2. So the total equivalent resistance for the entire circuit is the product over sum of this and this. Okay. So 8 times 5 over 8 plus. All right, that looks like, oh, it's the same thing I got before. It's the same thing. Right? So 2 different methods to get the same. Okay. Here we go. All right, you guys ready for number 6? Number 6? Number 6. Right. Oh, look at number 6, number 7. Look at those 2 circuits. Right? I mean, they each have 3 resistors, and there's a combination of series and parallel, but they're a little bit different than each other. I wonder what this would look like. I know I had these wired up earlier. So, ooh, yeah. This is this. Right? So, do you see how R1 and R2 in parallel with each other could be these 2? And then R3 could be over here. It looks like the leads of my battery or my cell phone charger may attach to, well, one is only touching R3 and the other is touching only R1, R2. Yeah, right there. That's it. What is this going to look like? Charger leads. And ooh, look at that. It looks like R3 is really bright and R1 and R2, they're on. There's electricity flowing through them, but they're really dim. Okay, I guess that. And of course, these resistors are all the same resistance. They're all probably a little over 2 ohms, I think is what we're getting the other day. About 2 ohms. Okay. So, okay. So it's like, okay, so what is the equivalent resistance though? Okay, so here's my voltage source. Okay, I'm going to start over on the opposite side, which is R2, okay, and then work my way back towards the source. So R2 and R1, are those series or parallel? Parallel. Okay. So I'm going to do product over sum of those two, or R1 and R2. So the resistance equivalent is 8 ohms, 10 ohms, 8 plus 10. That's product over sum. It's like 80 on 18, which is like 4.44 ohms. So it's as if there's a single 4.44 ohm resistor right here. Okay. Then I'm going to redraw the circuit. Voltage. Right. Now R3 I haven't touched yet. So on my paper says it's this many ohms. Go ahead and write that in there. R1 and R2 collectively is what I just calculated. Right there. Okay. Okay. And so you're working back towards the voltage source, run into this guy. That right there, is that series or parallel? That's series, right? So there's only one current. It has to flow through both sequentially, one after another. Okay? If you're driving around town, you have to go through that red light and also that red light. So that's series. So can I just add those two? Yeah. So the total equivalent resistance is that plus that is this many ohms. Yeah. All right, you guys get there? Is this working out for you guys too? Okay, number 7. Right, so this one has also 3 resistors. I can actually use this right here to hook us up. Right? So here I've got 3 resistors where I just tied all the leads together. Is that they're all tied together here and all tied together here? Is that? Right? And no. Scratch that. That's this one. Never mind. Mistake. Okay, start over. Do I have that? That's somewhere around. We just make this from scratch. 3 resistors. Let's put the. No, it's not a resistor. 3 resistors. Okay. So let's make this. So it looks like R1 and R2 are in series with each other. You guys see series right here? So let me go ahead and tie these 2 together. Oh, right. I'm just going to twist the leads together. I mean, these have been used for a few years, so it works. You just twist them and twist them. I do have some binder clips too. I might break out some binder clips later and clip them. Right. What's really helpful to use actually are alligator clips. I have some in the mail, but was late in getting those. So alligator clips are really good for putting them together temporarily. But I'm just going to tie these together. Okay. There we go. That's what I want. Okay. You guys see how this is going to be R3, and these 2 guys are going to be R1, R2. That's it. I just need to connect the leads. Bam, right there and right there. That's what I need to do. So remember what number 6 looked like? There was one really bright one and 2 extremely dim bulbs. What do you guys think is going to happen here? Ooh, I got one really bright one. That's R3, and 2 kind of medium dim. They're not nearly as dim as before, but they're dimmer. Right? Maybe that makes sense because the really bright one gets the full 5 volts going across it, and the kind of dim ones, it's probably like 2.5 volts, 2.5 volts. Do you guys think? Like that? Actually, I want to break out that multimeter. Let's do that. Let's break out that multimeter. Get a little bit of multimeter practice. I want to see exactly what is the volt drop across each of these resistors. Here, where's my clips? Binder clip. Binder clip. Try the binder clip method. what is the voltage drop across each resistor? And also, what is the current through any part of the circuit? So here. Okay, so now I got this all up. Of course, the paper is just asking equivalent resistance, but we're going to do a bit of extra practice on this one. Right there. All right. Multimeter time. All right. I find that poster with the multimeter. Okay, so I just made this poster last night. Remember, voltmeter, you're connecting in parallel because you're looking for a potential difference. Ammeter, you're connecting in series because you're going to force the current flow through the multimeter so that it can count how many amps. So we're going to start with volts. So leave the black lead, the negative lead, plugged in COM. The red one plugged in one says volts, so that's good so far. Switch this toggle over to anything at top left is volts, but I'm going to switch it to get the decimal about where I want it, which is like right there. Okay, that's too far. That'll work right there. That's decimal. Okay, and I'm looking for the voltage drop. Now, if I connect it like here and here, I should get about 5 volts drop. You guys think 5 volts? Right there. Okay. So that's exactly what I'll do right here. And then tomorrow, you guys will do a very similar thing. Here and here. .76. 4.8. I see 4.8. And now show a negative. If I switch the leads, it'll make it positive again. So let's switch the leads here. 4.8. I see 4.8 volts. Right? That's what I would expect it. What if I do this though? What if I go from here to here? Shouldn't that be about half of that? Maybe like 2.5 volts. You think about 2.5 volts. What happens if I go from here to here? 2.3. Or if I switch leads, I'll make it positive. Switch leads here. There we go. It's 2.4. You see 2.4 volts. Okay. Okay, so that makes sense. Okay. All right, enough of that. So just back to this page, figure out what is the equivalent resistance of this whole thing. Got switched off my multimeter. Let me show that too. Right. So, no, that's what else I was going to do. I want to get the current right here. Well, I've got the multimeter out. Let's do current. Current, I need to make a few switches. I need to take this out here, this lead out, and plug it in over here. One says amps. And switch this toggle over to the right. The one that says MA, like milliamps. So it's going to read how many amps. Okay. And also, I need to break open that circuit. So let me put my circuit back together. But I need to break it open to figure out how many amps are going to flow. So, notice. So clip this here. Okay. Now the other lead, okay, I would clip it here. Okay, that's what we've been doing. Okay. I'm going to break it open right here at the point of the lead. Okay, to see. Right, attach red to red and black to black. Okay. Ooh, do you guys see 3.7 amps? 3.7, 3.6 amps? Like that? Right? That's 5 volts. It's probably a little bit over 1 ohm resistance. You get like 3.6 amps. Okay. Now that's just with these particular resistors. Of course, on your paper, it's different numbers. Okay. Switch that off. Okay. Put that to the side. Might break that out another time later today so you guys can see that again. But back to this paper. So R1, R2 are in series, so I'm just going to add those two. So R1 and R2 resistance equivalent is 7 ohms and 8 ohms is like 15 ohms. Okay. Now that's not the whole thing, that's just a middle step. I'm going to redraw the circuit. Draw the circuit, voltage. Okay. R3 is this many ohms. R1 and R2 collectively are what we just calculated just by simply adding them together because they were in series with each other. Okay. Now working back towards the voltage source. Now these two guys, is that series or parallel? That is parallel. Okay. So the equivalent resistance, it would be a total for the circuit, is going to be product over sum. Product over sum. Right? You guys are following along, and you should get it course, an answer choice on the paper because this is going to be the final answer. Okay. Is it something like that? Bam, right there. All right. Are we good? So series followed by parallel. Okay. That's working out for you guys? All right. Let's skip number 8. I've just been doing that all day today. Let's hit this pair of questions right here, 15, 16, and then we're going to flip over and work on those waterfall models on the other side. Okay. So these two right here, 15, 16. Okay. Ooh. Wait, can I wire this up real fast? Wait, think. Well, maybe we'll just skip that. But let's just do the paper for this one. Okay. So R2 and R3, that I'm starting with those two because those are furthest away from the voltage source, right? R2 and R3. Okay. Is that series or parallel? Parallel, right? Parallel. Okay. So I'll do product over sum of those two, R2 and R3. Product over sum. So that's resistance equivalent is that many ohms times that many ohms over that many ohms plus that many ohms. Mine are 4 and 5 ohms, so do 4 times 5 over 4 plus 5, that's 20 on 9. That is 2.22 ohms. That's as if there's a single 2.22 ohm resistor right there. Redraw that circuit. Redraw the circuit. Voltage. Okay. Now R1 we haven't touched yet. So that's this many ohms. R4 we haven't touched yet. That's this many ohms. Now R2 and R3 together is what we just calculated. It's right there. Okay, we good so far? So working back towards the voltage source. Now we run into R4, which is this guy. Ooh, is that series or parallel? That's series. Right? Whatever current is already on this branch has to go through both of them sequentially, which means it's series, which means you can just add them up. Resistance equivalent is just add them. Right? Just like that. Right. Redraw the circuit again. Right? Back towards the voltage source. Those two guys, series or parallel? Well, that's parallel, right? Parallel. Okay. So the equivalent resistance is product over sum. This times this divided by this plus this. Product over sum. Okay. Should be getting an answer choice that's on the paper. Okay. No, that one's a bit more complex. So while you guys are wrapping that up, go back and recap that one. Okay. Found your voltage source on the left. You fly all the way over to the right side of the circuit, completely far away from the voltage source. Okay. These first two resistors, R2 and R3, are in parallel, which means you're going to do product over sum to find the equivalent resistance, which I did right here. Okay. Then redraw the circuit, an equivalent circuit. Okay. The next one you run into is R4 on top here, and that is a series relationship, so you add them together. Okay. Then redraw the circuit again. Now there's only 2 resistors left. They're both in parallel, or well, they're in parallel with each other. So you do product over sum and get the equivalent resistance of the entire circuit. So the battery feels like it's pushing against this much total resistance. Okay. Is that right? Are we good? All right. Now there's a follow-up question here, which asks about current. So current, let's break out Ohm's law. Current is voltage acting on resistance. This one's just saying what's the current flowing from the battery. Right? So let's do it. It got 5 volts acting on 2.2 ohms. It's like 2.27 amps. Bam. How many amps? Okay. Now that's the current that leaves the battery. Okay. But then you guys know that the current is going to go on this whole journey where it's going to split there, and it's going to split here again. Okay. All right, so you guys ready well, let's pause on the side of the paper. We'll maybe save some of these for another day. Okay, let's flip over to the side that looks like these waterfall models being set up. Okay. Okay. Now, you guys yesterday, I think I got a little bit ahead of my other classes because we hadn't quite done this column. So I'll recap this column, which is probably a good thing to do anyway. Okay, and then we'll go on from there. Okay. So we're trying to figure out what exactly is the voltage drop across each individual resistor, and then later on, what is the current through each resistor, the current at any point in the circuit, okay, and then what is the power, like the rate of energy across each resistor. Okay, let me go ahead and draw the waterfall model for this. Okay? So you can break out different colors. I'll call these voltage planes. I don't think that's a textbook term, but just call it that. Like this battery is going to pump up so many volts. My battery is 12 volts. You guys see my battery is 12 volts? Do you guys see how many volts your battery is? Okay. So mine's 12. Here's something. Right? So it pumps up 12 volts. Okay. Then maybe I'll have like a blue plane. Right. There's going to be a voltage drop across this resistor. Then there's going to be another voltage drop. Okay. And finally, it's going to drop all the way down to 0 volts, like that. So what does this look like? Okay, we got this pump pumped up to like 12 meters tall, you can call it, but it's like 12 volts. Okay. Then there's this waterfall, a splash, which represents some voltage change, delta V, which actually, since we did it yesterday, you guys see it's just going to be 6 volts, equals 6 volts right there. Okay. Then that's going to dump down into this blue plane. Okay. Then we got another voltage drop. Okay. Now, yesterday we calculated 4 volts. I'll write that on the paper, how to get these, in case you need to say that again. Okay. That's going to drop down to this yellow plane. We got another waterfall, another voltage drop, which on my paper came up to be 2 volts yesterday. Okay. And then we're down to the green plane, which is like 0 volts. And then it gets pumped back around to the battery, the pump, the battery, okay, it gets pumped back up again. Okay. Do you guys see my battery is like 12 volts up, and we got 6 down, 4 down, 2 down. That's like 12 up, 12 down, 12 up, 12 down. That is Kirchhoff's loop rule. That's this one right here. Okay, just says the sum of the waterfall's heights has to be the battery height. Okay, makes sense. The pump height. Okay. Right. So how did we figure out yesterday? Figure out the numbers that are already on the paper. Okay. Now, the fact that these are all in series, you can very simply add each individual resistor to get the total resistance. So in my case, 3 plus 2 plus 1 was 6 ohms. Okay, so we figured that out. Okay. But what about the voltage drop across each one? Now, if I ask you guys, where do you think the voltage drops more, across a large resistor or a small resistor? You say, oh, well, the large resistor. The more the resistance, the more the voltage drop. And that's exactly proportionally true. That's a direct proportion relationship. That's this one right here. Okay. So I'm going to break out this rule right here, this one right here. And I'll write that down on paper, and that'll bring us up to, I'll show you guys how we got those numbers. So what was the voltage drop across resistor C? I'm going to do resistor C itself, here, resistor C over the sum of the resistances, all times the voltage across the battery. How about that? So across resistor C, resistor C itself was 3 ohms. The total resistance was 6 ohms, the sigma right here, somehow. And the battery voltage was 12 volts. Okay? 3/6 is half of 12 volts is 6 volts. That's where this 6 comes from. This is 6 volts. Okay? The drop across resistor B was, well, the resistance was 2 ohms. And again, the total resistance along that branch, which was the entire circuit, was still 6 ohms. Multiplied by the original 12 volts. 2/6 is a third of 12 volts is 4 volts. Oh, that's where this 4 comes from, 4 volts. Okay. What about the 1 ohm guy? So the drop across resistor A, 1 ohm compared to 6 ohms of the 12 volt total is 2 volts. Oh, and that's where that 2 comes from, 2 volts. Okay. You guys remember that from yesterday? Right, and that's about where the bell rang. Okay. Okay. All right, so as long as they're all in series like this, the total voltage drops should add up to the total voltage of the battery. Again, that's just the loop rule, right? So 6 plus 4 plus 2 is 12. So we're all good. Right? And that works for you guys too, right? It works out. That plus that equals that. Okay. Next column. What is the current through each individual resistor? Isn't this Ohm's law? Ohm's law? I equals V over R. Ohm's law. Oh, there's the V, there's the R. So the current through resistor C, I got CBA, so we're going to see first. Through resistor C, I got 6 volts acting through 3 ohms. That is 2 amps. That 2 amps right there. How about the current through resistor B? Well, that's 4 volts on 2 ohms. Oh, that's also 2 amps. How about the current through resistor A? That is, I have 2 volts acting on 1 ohm. That's still 2 amps. Interesting. Yeah. And then what about through the battery? Now the battery itself, the current supplied by the battery, well, the voltage supplied by the battery is 12 volts. And the equivalent resistance it feels like it's pushing against for the entire circuit is 6 ohms. That's still 2 amps. Right? Right? So it looks like the ratio of voltage to resistance was the same current for that entire setup. Okay? Now that should be true for every single series setup. That's not going to be true for the other tables, like the other setups. But regardless of what numbers I gave you on your individual paper, you should have the same number copy pasted all the way down that column. Is that true? And here, look at this. There's only one stream of water. Okay? So if it was like 2 gallons per minute here, it's 2 gallons per minute here, 2 gallons per minute here, 2 gallons per minute here. It's 2 gallons per minute everywhere. Okay? It's like 2 amps. Okay? That is this rule right here. See, as long as you have a series setup, the current is the same everywhere, because it never splits. So it has to be the same everywhere. Right? It's like a conservation of charge idea, conservation of charge flow. All right, very good. Okay. How about this last column, power and watts? Power and watts. So we're going to go over to Joule's law. In Joule's law, there's these 3 perspectives. You could go current times voltage. You could go current squared times resistance. Or you could go voltage squared divided by resistance. And they'll all tell you the same thing. Sometimes one's more convenient than the other to use, but I'm going to do all 3. I'll show you guys that they all come out to the same thing. So for resistor C, let's say for resistor C, I times V, I got 2 amps times 6 volts. Is that like 12 watts? I see 12 watts. I could have done this though. I squared times R. So that would have been 2 amps squared times 3 ohms. 2 squared is 4 times 6. Oh, still 12 watts. Still 12 watts. Right. Or I could have done voltage squared over resistance. So the voltage drop across resistor C is 6 volts. Square that and divide by 3 ohms of resistance. 6 squared is 36 divided by 3. Oh, still 12 watts. So you don't have to do all 3, although maybe it could be good to check your work, but just pick your favorite way and you're always going to get the right answer. As long as you do it right. That many watts. 12 watt bulb there. You guys get that? So there's 3 different ways to do it. Pick your favorite one. Now let's go over to resistor B. So that's for C. Right? We just did C, right? Power B. Maybe I'll just pick one of them. So I'll do I times V. How about that? I times V. So I've got 2 amps across a 4 volt drop, which is like 8 watts. That's 8 watts right there. Okay. And the power drop across A, or the power consumption at resistor A. Let's do I times V there. I still got 2 amps, but now there's only a 2 volt drop. 2 volts. And that's like 4 watts. Like 4 watts right there. Okay. 6 times 2 is 12. 4 times 2 is 8. 2 times 2 is 4. See that? Just multiply the previous 2 cells. Right? Every good so far? All right, okay. All right, now the last cell in this whole table. You guys ready for the last cell in the whole table? Okay, so this one, we give you guys two different perspectives on this, two totally different perspectives, but they should give you the same number. And if you did this whole table correctly, then you'll get the same result no matter how you do it. One way is I could just focus on this row, what's going on strictly with the battery, and I could apply Joule's law. Guys, what's 12 times 2? 24. Yeah, so I times V, that's 24 watts. That's got to be the answer on my paper, 24 watts, right? I times V, just like we did the previous rows. Right? Or you could think about it in terms of electricity supply, electricity demand. Like these three resistors are collectively demanding how much electricity. What's 12 plus 8? 20 plus 4 is 24. It's the same thing. It's 24 watts no matter how you do it, right? So let's say that again. So you can try it on your paper. You can do I times V, right? 2 times 12, 2 amps times 12 volts, right? Get 24 watts that way. That's Joule's law. Or you can think about electricity supply, electricity demand. So I got 12 watts demanded there, 8 watts demanded there, 4 watts demanded there. That's 24 watts demanded. So there must be 24 watts supplied so that it balances. Okay. Right? Is that working out on your guys' paper too? Working out? You guys good? All right. Are we good so far? All right. Let me break out the multimeter. I think it's a good place for that. So tomorrow, you guys could construct this if you like. So do I have 3 in series somewhere? 3 in series. Well, here, I can make this 3 in series. No, here, let's try some new ones. Look at all these in series. Let's do 3 in series right here. Boom, there's 3 in series. I see 1, 2, 3 in a row. 1, 2, 3. Okay. Now, of course, that's about 2 ohms, 2 ohms, and 2 ohms. So they don't, the numbers don't match exactly, but we're going to get some more multimeter practice. Okay. I break out the, where's that page? It says, oh, here it is. Here it is. Okay. So you guys remember this. So tomorrow, you really need to know this, right? When you're measuring volts, connected in parallel so you can measure a potential difference. When you're measuring the current in amps, break open your circuit and force the current to flow through the ammeter, right? In series, connected in series, right? So parallel series. Okay, so that's what we're about to do right here. I got my 2 leads on my cell phone charger. Bam, bam. Okay. Ooh, this lights up, but they're all kind of dim, but maybe you would have expected that, right? Because they're all in series, right? So there should be a 5-volt difference from lead to lead. Clip these on here and see if that's the case. Is it 5 volts across the whole thing? And then if I do individual resistors, what are the individual voltage drops? And it should be about 1/3 of that for each one, or 5/3 of. Okay. So I got this hooked up. All my bulbs are on. Okay. First thing, let's do volts. So if I want to get volts, the potential difference, I just turned off. I kind of flickering. Twist this thing. There we go. Okay. Ooh, that's a good thing you can do. Here, hot tip. If you clip on a binder clip and you twist it, see how I twist it like this? Okay, it'll tie it together better. Okay, so other stay on. Okay, so I have to pop this out, switch it over to the one that says volts. Okay, you guys see those two? Okay, so tomorrow you guys are going to do that, right? Everybody follow that? You're going to do that tomorrow? Okay. Switch this toggle over to volts. I'm going to move this decimal place to probably right there. That's probably pretty good right there, right? Okay. And 2 leads. Now across the whole thing, I'm expecting pretty close to 5 volts. Let's see. 4.8. It's negative, so let me go ahead and switch the lead so I just get positive. Oh yeah, red to red, black to black, right? There we go. 4.8 volts. 4.8 volts. Right. What do you guys think it is from here to here? Here to here. Should be about 1/3 of that. What is 1/3 of that? About 1.6 or so? Let's see if it's 1.6. It's hovering around 1.6, 1.7. Is that? Right. What about from here to here? 3.2. And then again, the whole thing. It's like almost 5. Well, it should be. There you go. 4.8. Okay. I guess that. Okay. What if I want to get the current going through this thing? Again, there's only one current. You guys just saw it because it's all a series. I got to make some changes. Yeah, pop this out, move it over here, switch this toggle to the one says MA. Okay, so it's going to measure amps. Okay. And you need to break open the circuit, which is the bulbs are going to turn off, and then connect this in series to it, and the bulbs are going to turn back on. Okay, so take off this binder clip. Now my bulbs are off. Okay. Let's go red to red. Okay. And then this black lead, I'm going to hook to the bulbs, and the bulbs should turn back on. And they do. Oh, look at that. Do you guys see about 1.2 amps? 1.2 amps. You guys see? Okay. So yeah, tomorrow when you guys are getting empirical measurements like that, like I just showed you, then I'm going to give you guys a lab page that looks pretty similar to this. It's going to have this type table. Okay. You say, well, the current across each of these was well, if it's all series, it could just be the same number all the way down and go at 1.2, 1.2, 1.2. Okay. Turn off the multimeter. Okay. There's just a battery in here that I just found it is quite hard to change out. So if you guys switch that off, that will preserve the battery life, and I will appreciate that. All right. Questions so far? You guys are good? All right, let's skip number 2, number 3. Those are a little bit complex. That's all right. Let's go number 4. Number 4 is the most straightforward, next most straightforward one. They're all in parallel. See how they're all in parallel? Okay. So what does the waterfall model look like? Let's start with that. So I'm thinking that there's 2 voltage planes. Okay. It's pumped up to so many volts. I still have a 12-volt battery. You guys have how many volts your battery is. And then the voltage is going to drop across these resistors to like 0 volts. And it's going to go back to the battery and get pumped up again. Okay? The current splits 3 ways. That means I'm going to have 3 side-by-side waterfalls. So one here, one here, one here. Okay? And then waterfall, 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 a splash. Okay. And then this green voltage plane, which is down in the valley, all this water is going to reroute back to the pump. Get pumped back up again, and round and round it goes. Okay, waterfall model. Okay, guys get there? Okay. Do you guys see that these are all going to have the exact same voltage drop? Right? Delta V is the same, which is whatever the battery is. In my case, it's 12 volts. I have a 12-volt battery. These are 12 volts up, 12 down, 12 up, 12 down, 12 up, 12 down. You guys see that? You can fill in this column right here. 12 volts, 12 volts, 12 volts, or whatever your battery is. Mine's 12 volts, so it's going to be 12 volts regardless. Okay, that is the loop rule. But here's the version of the loop rule for parallel. If you have 2 resistors in parallel, it's always the same voltage drop because it's always the same height waterfalls. Right? Even if they're different resistances. If they're different resistances, then the current will change. Right? So the smaller resistor, there should be more current going through it. And the larger resistors, there should be less current. But they're all the same voltage drop. Okay? Might have a wide waterfall and maybe some skinny waterfall. Right? Oh, we didn't get the equivalent resistance. So let's do that. Now, since they're all in parallel, could I use the reciprocal method? It's like 3 guys painting a fence, right? This guy takes 3 hours. This guy takes 12 hours. This guy 12 hours. I bet if they teamed up, 3-man team, they could knock out that job in probably 2 hours, I'm thinking. Right? Let's see. So 1 over the equivalent resistance is 1 over the first resistance plus 1 over the second resistance plus 1 over the third resistance. Okay? You guys are doing this too? All right. I'm just going to use a calculator. Let the calculator crunch these fractions. Right, so 1 over the answer, whatever it is 0.5. That's 1 over ohms. Kept my unit. Okay. One more step, though. One more step. You still have to take the reciprocal. So the equivalent resistance is 1 over that, which is like this many ohms. Okay. So you still have to reciprocal. Okay, so that is the equivalent resistance right here. 2 ohms. Okay. Let's got about a minute left. So let's do this last bit a little bit faster. I is V over R. 12 over 3 is 4 amps. V over R, 1 amp. 12 over 12, 1 amp. I just did V over R, right? Did ohms all the way down. Okay. 12 over 2 is 6 amps. Now, the fact that the current splits, now this is a different setup than the series setup, the parallel those, right? If the current splits, I'm gonna have like 4 gallons per minute here, 1 gallon per minute here, 1 gallon per minute here. That means the battery must be supplying 6 gallons per minute, right? So that makes sense, doesn't it? That the currents should add up. In series, the currents had to be the same all the way down, but in parallel, the currents have to add up. Okay, so, all right, we got about 30 seconds to the bell. So tomorrow, I'll finish this table with you guys, and then I'll get you guys started on the lab where you guys get to break out the multimeters and the Christmas lights.